Hi, welcome to a quick introduction to the use of mass spectroscopy, a very valuable tool. And we're going to use this and apply this to isotope abundance determination. So, real quick overview of the equipment. This is kind of a very simplistic schematic of this. What we do in mass spectroscopy is first you're going to vaporize the sample. So you've got to get the sample to the gaseous phase. Then you're going to bombard it with electrons. So electrons are going to go through that. And what you're going to do in doing that is you're going to ionize. You're going to kick off electrons. You're going to make cations primarily. Okay, there's gets much more complicated when you deal with molecules. So I'm talking at a very simplistic level. We're going to look at this as if the vast majority are a +1 ion. All right, and so now we have a bunch of +1 ions. But what is going to differ amongst all of these, if they're isotopes, is they will have a different mass to charge ratio. So once you've ionized and we have these ions, they're going to go through some plates, charged plates that will accelerate these cations. And then they're going to go through a magnetic field. So this magnetic field is going to select our particular ion. So the ion we want, you tune that magnetic field so it makes it to the detector and impinges on the detector, causes current flow. Right? Now, if the ions are heavier than what we want, they're going to be deflected down. And if they're lighter, so they're going to be deflected less. So the lighter ones get deflected more, the heavier ones get deflected less. All right? Sorry about that. I misspoke. So lighter ones have a longer arc because they are easier to move. You can think of it that way. And then the heavier ones are deflected less, but the point is we get to collect a particular isotope. So then we can tune this magnetic field so that it selects that particular mass to charge ratio that we're interested in. Now, in an idealized spectrum, spectra is plural, spectrum is singular, and in an idealized one, you'll be able to read the percent abundance right off of the axis. So you could call that the absolute abundance, the true percent abundance. But truly in a mass spectrum, what you're going to get are relative peaks. So the height of the peaks will all be relative to the most abundant. Now, with any good piece of equipment, I haven't done any mass spectroscopy, but it seems to me it would not take much to program this to convert it into a scale where all you would have to do is read the values right off of the y-axis. I wanted to show you this one because it's a little bit harder. So, and not too much, but just a little bit. So what you would do is you would add up all of your percent abundances. And in this case, that happens to be 135.6. And then we simply have to set up proportionalities. So in this case, for the first one, I have 11.2 is to 135.6. Well, I don't want that out of my total. I want my total to be 100, a pure percent scale. I want the sum of all my percentages to be 100. So if I solve for that, I would get 8.26 for that mass to charge ratio of 46. If the charge is +1, we're effectively looking at the mass from that x-axis. And I would do the same for the next one. Let me do the second one down. I would have 100 over 135.6. But I want the total scale to be out of 100, so I would have to solve for that. And as you go down the list, I have 82.6, then I got 7.45, 73.75, then 5.38, and then 5.16. You add those up, and we should, within rounding differences, get 100. Okay? So now that I have that, those absolute percentages, I can find the average atomic mass of titanium. And that is the fraction mass, so it's 8.26 over 100 times the mass number of 46, plus the fraction mass. You can go ahead, some of you might want to do that in your head and not write it as the fraction. You might want to write it as 0.0745 right away, the fraction, and that would be fine for my class. I don't know what your teacher or professor wants. Times 10.1 plus, I'm just trying to make a point that to get to the fraction, you simply take the percent and put it over 100, and then that would be, whoops, I looked at the wrong number there. Let me fix this, sorry. Oh, Dena moment. So that would be times 47. Sorry about that. And then this one would be times 48 plus 5.38 over 100. I think you get the point. Plus 5.16 over 100 times its mass, fraction mass plus fraction mass plus fraction mass. Okay? And add that up, and you should get very close. It's an experiment, and we've rounded. You might not get exactly what's on the periodic table, but you should get very close to what is on the periodic table. And that is how scientists would determine isotopes. So if we found a new element called denzelium, we could use mass spectroscopy to determine the percent abundance of its isotopes. Okay, thanks for joining me. Have a good evening.